Hi, welcome to another edition of Calculus 3. Today we are going to talk about arc length and curvature. Let's go ahead and take a look at this very interesting and a bit advanced topic. So, we have talked about arc length before. We have learned how to calculate the arc length. The question is how to use that to parameterize a curve. What do we mean by parametrization of a curve? So suppose a trucker is on a highway and he's going and he's supposed to record his location. So the most common way of doing this is to say at a certain time I am at this location. So at 1 o'clock I'm at this city, and at 2 o'clock in the next one, and at 3 o'clock in the next one. That is that's a parameterization by using time. So you are giving your location x, y, z or GPS coordinates or whatever it is in terms of time. Sometimes it makes sense to give your location in terms of an angle. So obviously if you are going on a circle, you can specify that your location is such and such in terms of a central angle. What we have in mind now in this section is how to parameterize a curve with respect to arc length. What is the meaning of this? Suppose a trucker is on the road, or perhaps better example than that is a person who is hiking on a trail. So he could be walking around, wandering and so on. And he wants to say, after I have walked for 1 mile, my location is such and such. And after I have traveled for 2 miles, my new location, my new position is such and such coordinates. So he's giving his position in terms of the amount of distance he has walked. So you can imagine somebody hiking up a mountain and such might use such a style of giving his position. Sometimes we want to go back and forth between these kind of parameterizations, and we are going to practice that. Next topic we have in mind, which is in relationship to parameterization based on arc length, is how to define and calculate the curvature of a road. This is a concept that is intuitive to us. We want to make it formal. So if you go on a tight circle like this, you say you're going on a tight turn. But if your car takes a very big distance to turn a bit, you are going to say you are in a wide turn. For this kind of a situation, we associated small radius to that. With this situation like this, we say a large radius connects to a problem like this. When we use the language of curvature, something that is tight like this, we say it has a large curvature, and something that is smooth like this, we refer to it as something with a small curvature. So we have a sense for what this thing is, but the question is, well, how do you formalize it? How do you actually calculate a number that connects to curvature of a curve? And it turns out to be a bit more advanced than the other things we have done. Okay, let's go ahead, get started. We are going to do some example, give some formulas today, and then the main proofs and such is going to be delegated to an additional lecture that's going to be much more detailed than this one. Okay, so going back to what arc length is. So from Calculus 1, you remember that if you have a curve and you want to find out how long it is, well, the best way to do that is to approximate it by a polygon. So you choose a bunch of points on this thing and then connect these points and then measure the length of that polygon. Well, that's a good approximation for what the curve is going to be. Well, what if I want a better approximation? Well, I increase my number of points and patiently I calculate all of these line segments and add them up. Well, in the process of calculating the line segments, what do? Most common thing to do is to make a right triangle. So here we have our coordinate system. In that coordinate system, we come across any of these line segments. The horizontal displacement here traditionally is referred to as delta x. The vertical displacement is called delta y. And if we were in a three-dimensional situation, there would be a delta z as well. Well, the hypotenuse is what we are after. That hypotenuse is going to be shown by delta s. Well, the relationship between these three things is very standard. That's just the Pythagorean theorem. Delta s squared is delta x squared plus delta y squared. Okay, as simple as just the Pythagorean theorem. Now, well, if you, of course, you want delta s, you will be taking square root, and that would be these items inside that radical. Well, when you want to do this thing in calculus, of course, you go ahead and you give your x and y in terms of some parameter. That's where the parameterization comes in. And then once you have that, so for example, if your x is given in terms of, say, time, your x is a function of time, your y is also a function of time. We said that's like the example of a trucker who is using time to indicate what his position is. Well, then delta x will be approximately, let me just use the equal sign here so that my writing will be clean. It will be x prime, that's a derivative, times delta t. So this is actually an approximation, but it's fine. Same way with delta y. That is y prime delta t. And then when we stick these things inside this radical and take the delta t out, and also use the notation of a differentials to get ourselves for integration and such, we are going to have the following. We are going to have ds. So instead of delta, which is an approximation, we are using ds for the differential, and then inside the radical I'll have the x prime squared and the y prime squared, and this delta t also is going to be written as a differential. So this is the formula for the differential of length. What is this red thing in terms of the delta x and delta y? That is what that is. And if I want to figure out what the length of the curve is going to be, I'm going to integrate whatever this expression is. Let me do away with my parentheses so that I can write faster and also not to clutter this. Well, your trip starts at some time, let's call it t1, and ends up at some time, let's call it t2, or t start and t end. And if you want to find the length, you go from beginning to the end of that, and that is your length. Well, if you were in 3 dimensions, story will be same, just that you have more things to deal with. So t1 to t2, integral of, then you have x prime squared and y prime squared and z prime squared. So you have 3 things to worry about. This formula might look a bit intimidating and such, but in fact it's something you learned way back in elementary school. You remember that you had the concept of speed. What did they tell you way back when? Maybe 10 years ago. What was the speed? The ratio of 2 well-known quantities. Well, obviously distance over time. Distance over time, this is really just that. How so? Well, this sum up square of derivatives in square root, that is just the speed. Who is this? This is your time. What is that? Well, on a typical road you have different speeds at different times, so you multiply speed by the length of the time during which that speed was effective, and then you add them up. So if on a section of the road it was traffic, you're going at a low speed, a certain length of time, you multiply them, and then the traffic clears, your speed much higher, and then multiply by the time during which that speed was effective. You just add them up. So this is simply means add all these little pieces. And what is this? What S is the distance traveled. This is distance, which we are now giving it another name, which is arc length. The distance you are traveling is the length of the arc you are dealing with, assuming you are going in one direction. So that is really the formula we have. Very simple. Let's write it in a bit more advanced style as well. So I say S is the integral of from some time to some other time. This is R prime in absolute value. So what happened here? What happened? R is a position. R typically is representing positions X, Y, Z, or as sometimes is written X. Let me just remind you, sometimes we use this notation of I, J, K, and then if you are using the software, you have to somehow indicate that these are unit vectors. You typically write them in bold or something. Same thing. Anyway, then R prime, the derivative, is going to be the slope or speed in X direction and speed in the Y direction and speed in the Z direction. So that's X prime, Y prime, Z prime. So that's going to be velocity. When you take the velocity and take the absolute value of that, absolute value, how do you do absolute value? You square them and take square root. That's what becomes our speed. So if you can think about this thing several styles. Instead of R prime, I can write it velocity in absolute value. That would be the same thing, T1 to T2. So think about it this way. Distance is equal to the integral of speed versus time. That's what it means. Let's go ahead, do a simple practice. Suppose I have say we want to find arc length of a helix given by R of t is equal to say 2 cosine of say 3t, 2 sine of 3t, and say 8t. From t is equal to say pi third to t equal to pi half. Okay, helix is a very nice 3D picture. We use it a lot because it's easy to work with, it's easy to visualize. Let me just go back. We have looked at this thing several times before, but just look at the helix one more time to see what we are talking about. So on this page you go ahead and choose a space curve, and then it gives you x, y, z. You see it's parameterized by something. We just call it the t. In this case, I've written here just very basic cosine t, sine t, 0.1 t, just so that everything fits here. And well, we get this curve that looks like a, you can think about it as a slinky that has been opened up, spiral staircases. You see it in some emergency exits at the side of tall buildings. You see it next to tanks in in refineries and such. You see a lot of example of these things. So well, here I am just showing the velocity on this as I am moving around it, so that you have something to focus your eye on. We are going around, you go up, and you notice I am tracing it versus this t, and the question is, if I go from some t to some other t, how much of the length of this curve have I covered? That is what this problem is after. What is the distance I have traveled if I go from one place to another place? Well, again, we go back to that elementary school formula. It's really speed times time. You add them up, and then you will figure out how much you traveled. Well, a little bit more than what you did in elementary school, because you need to calculate velocity, and to calculate velocity you need your derivatives. So all of a sudden you're talking about calculus. So we have here r prime, so I go ahead and calculate r prime. I have to take a derivative of this, so of course we need to know how to differentiate. Derivative of cosine is minus sine. Chain rule gives me another factor of 3 inside, so minus sine sine of 3t. Derivative of sine is cosine, another factor of 3 comes out, 6 cosine 3t, and derivative of 8t easily is just 8. Then so this is, let's remember, this is velocity, and then what is the speed? I need the speed. Well, that's the absolute value of the velocity. Well, how to take absolute value? Square these things and add them up. So minus 6 sine 3t, you square that, and 6 cosine 3t, you square that, and 8, and you square that. Add them up, take square root. Well, of course, my 6's get squared, so that becomes 36. Sine, I will have a sine squared minus cos of a, sine squared, and then cosine squared. So let's just put them together and factor 36 out of both of them. And this one is, of course, my 64. And then we need a small piece from trigonometry. What is sine squared plus cosine squared? Of course, that is just 1. And then you have 36 plus 64. That's the nice thing about the helix. This thing just becomes a number. T goes away. That's the magic of helix. Most often, for just an arbitrary curve, these things get stuck on the radical and problem becomes complicated and such. But here we went after the easiest thing. So this becomes, of course, 100, and another lucky day, this is just a 10. So while I'm going on that helix, my speed is constant. Of course, my velocity, I'm turning around, my vector is turning around, but my speed is fixed. That is going to make my life a lot easier, because when I want to talk about the length that I have traveled, or the distance, so the distance in terms of not the distance of the two endpoints, but the arc length that we have traveled, the arc length, how much we have walked or flown or something, that would be the integral from the beginning time. So my beginning time here became pi third. My ending time is given to me as pi half. And then I'm supposed to have my r prime here and dt. Now I got lucky that my r prime became as easy as it could be, just 10 dt. Well, what's the antiderivative of 10? Well, that is obviously 10t. And then I am going from pi third to pi half, so that is going to be what, 10 times end minus beginning, and this difference is pi 6, 10 pi 6, that is the length I have traveled. So as simple as that, we are in this case we found out what the length of the curve is going to be. Now next question up is, well, how would you change this thing to the parameterization that we had with respect to the arc length? let's take another example. So separate example similar to this, but let's make it 2-dimension. So this time I ask parameterize the curve. This is a 2D curve. Let's take it as, say, x is equal to 6 cosine of 3t and the y is equal to 6 sine of 3t by arc length. And well, if you want to parameterize by arc length, you want to specify what is your 0 point, what's your starting point, and also in which direction to travel. So suppose I want to take x, y, 6, 0 as a starting point and travel in a counterclockwise direction. So counterclockwise, the issue of which direction you're turning. Well, x equal to that and y equal to that. Of course, when you square them and add them up, you get x squared plus y squared is equal to 6 squared. So that is a parameterization for a circle. So they might have given us the circle from the beginning. So from get-go, I have a circle. This curve is a circle. It starts at this point. Okay, it says start at 6, 0. 6, 0 is just this point, and travel in a counterclockwise direction. You know, I could have gone this way, I could have gone the other way, and say, well, here is saying, well, go in this direction. So we are going on this circle, and what is it that we want to do? We want to say, give me your location, but tell me your location in terms of the distance you have traveled. Like after you have traveled 1 mile, tell me what's your x and y. After you have traveled 2 miles, now tell me what's your x and y, and so on. So give me what we want is to find x of s and y of s. Okay, how do we do this? Very simple. We said in the previous episode that s is integral of r prime versus whatever variable you had starting at the starting point. So that is rather arbitrary. So we are going to set this thing at r0. So we are going to start at displacement 0. We are going to start this at r0, and then we are going to go as far as time t, find out what's the distance we have traveled. Then the plan is to figure out what the time is going to be in terms of the distance we have traveled, and just do a simple substitution. So let's go ahead and do this. So I say s is equal to integral from 0 to t of r prime. So r was x and y here in 2 dimensions. R prime is just x prime and y prime. Just differentiate these two things. So my r prime is going to be minus 16, minus, forgot my multiplication too, minus 18 cosine of sine of 3t, and then 18 cosine of 3t. Okay, when I differentiate these two, sine became cosine, cosine became minus sine. By change rule, each of them got multiplied by 3. R prime in absolute value, which is same as the velocity. So this is just the velocity in absolute value. This is velocity. Well, I have to square these two and add them up, and again in this very easy example, when you do that, you just get 18. Is that right? Because when you square sine and cosine and add them, you get 1. So let me write down all the steps so it doesn't look like we just pick a number there and put it there. Like, okay, you have to do minus 18 sine of 3t and square it, and 18 cosine of 3t and square that and add them up. Sine squared plus cosine squared becomes 1, so that's a magical simplification, and 18 squared from radical comes out, becomes 18. So this is 18 dt. Well, 18 dt, when you integrate it, it's 18t. From 0 to t becomes simply 18t, which then tells you the time is s over 18. So this is a way of telling time based on how much you have walked. If you tell me how much you have walked, I divide it by 18, I will know what time it is. Well, what are you going to do with this? Well, I know the time. I replaced my time with that. So I'll have x. It was previously 6 cosine of 3t. Let's see, 6 cosine of 3t. Now it becomes 6 cosine of 3. Instead of t, I put s over 18. And same with y. So y was 6 sine of 3t. Now it's 6 sine of, well, s over 18. If you want to clean it up a bit, 6 cosine of s over 6. And this one, well, 6 sine of s over 6. Okay, so this is our parameterization. That's what we were after. What is your location? X and Y. Here's my location. 6 cosine. Take the distance I traveled, divide by 6. Cosine of that, multiply by 6. And then same here for the second components. S over 6. This is a parameterization by arc length. So arc length is intrinsic to your curve. Time isn't intrinsic. That's a difference between these two. Like if I have one runner and another runner on this circle, on a lap or something, then their location will be depending on how fast they're running. So one runner and another runner are going to have a different parameterization because their speeds are different. But when I parameterize in terms of arc length for both of the runners, I'm going to end up with the same answer. If runners are going in this direction, both of them, at the end for both runners, when I come to my parameterization by arc length, I'll have the same formula. So we say this parameterization is intrinsic to the curve itself. It's not depending on what that runner is going to do out there. There's one very important property of this thing. So by now, let's go ahead and write this thing. We call it R of S. Previously it was always R of T. Okay, these things were functions of time, but now we have R of S. S is R, arc length. The one property of this thing is that if I differentiate this, let's go ahead and differentiate, and just like any other place we can get a concept of velocity. If I differentiate, you notice a factor of 6 comes out, cancels this 6, and I get a minus sine of S over 6, and again here this 6's cancel each other, and I get cosine of S over 6. Do you realize what is the big property of this? The big property of this thing is that if I calculate the derivative with respect to the arc length, and take its absolute value, well, sine squared plus cosine squared is 1, and square root is 1. That is always true regardless of what type of a curve I'm traveling on, or what the runner was doing, and so on. In all cases, it's true that the derivative of, so here we have a general observation to make. If you have your position, you parameterize with respect to arc length and take a derivative of this and calculate the absolute value of that, you always get 1 regardless of the curve that you had or how you were originally parameterized it or traveled on it. Why so? Well, let's go back to our original picture. When you go from one location to another location, your dr is this this vector. ds is the length of this piece of your curve. Well, the length of this vector and the length of the arc length are close to each other. At the limit, when you're taking this derivative, the ratio is going to tend to 1, simply because you parameterized your curve with respect to arc length. So this is a important property of this parameterization. I want you to think about it and hopefully agree that that is the case. Okay, what are we going to do with this topic? Is significant by itself, and a major application of this thing comes in calculation of curvature. So next topic up is how to define curvature. So we said it's very intuitive that if I have these two curves in front of me, I can visually say, well, yeah, this is a tight turn, this is a wide turn, this is a small radius, this is a large radius. Then the concept of curvature is taken to be reciprocal of the radius. So this one, if you think about it as a circle, it's like a tiny circle. We say it has a lot of curvature. It's okay, it's wound up, as opposed to this one. So if I try to graph this thing, so this one has a large radius, and large radius we associate it with a small. So let's write this thing. This is a small radius. This one is a large radius. So for example, your lawnmower is turned on a very small circle, but if you have an 18-wheeler, well, you better have quite a bit of space to turn around. And then we turn this concept on its head and make another concept. We call this thing something with a large curvature, and this one with a small curvature. So how are these related to each other? The radius is going to be reciprocal of the curvature, or other way around, curvature. So this concept is rather easy to see what it is, and the formulas of it are going to be a bit more advanced than other stuff that we have seen. We have gone through one episode of similar type of formulas in a previous lecture, but this is going to be building on top of that. So let me go ahead and show you an example of what this thing looks like before we drown ourselves into the formulas. So this one will be better perhaps. So here I have a curve in just plane. This is going to be an ellipse that you can parameterize ellipse with sine and cosine. As soon as you choose two coefficients that are different from each other, you'll get an ellipse. If you choose the coefficient the same, you get a circle. Now what this software does also, nice thing, it is showing us so-called oscillating circle, and you can ask for what the curvature is going to be. This is a strange name. Oscillating, in Latin I guess it means kissing circle, so you didn't think mathematics is going to have NC-17 type of terminology in it, but well, that's what it means. That's I guess it was Leibniz idea to call it that. But anyway, let's go around, see what happens. So at each point of this curve, so my main curve is this red elliptical one, we can define this circle. This circle is called the oscillating circle. The radius of it is the radius of a curvature. The reciprocal of that is going to be the curvature we are after. Now as I go around, you notice that at this edge of the ellipse, the circle that approximated is much bigger, so the curvature is going to be smaller. You see, here's a curvature at this end, about 2. When I go in that middle right here, the curvature is about 1/4. And the question is, well, how do you come up with these numbers? How do you come up with that circle and so on? We are going to go back to calculating it, but before we get there, so you can read about oscillating circle and the history of that and what it means and so on. And this picture perhaps is going to look a lot nicer on your arm terminal, and here it's going to be a little bit hard to see as to what it is. This is a spiral, and somebody has drawn all the oscillating circles of it, and you see that you get a nice pattern. At any rate, let's go back to how do you do this? Well, it's very intuitive actually. The definition is take a unit tangent vector and trace it to see as you go around how much does it change. So here you see that this tangent vector was pointing this direction, and I went a little bit, and then it is changing this much. Here, to compare apples to apples, I take the similar unit tangent vector, so I take this to be of length 1, so that is the same thing, and then I travel by the same distance I traveled here. So whatever this is, perhaps this much, I travel the same amount here. Now I'm going to check to see how much did this thing change. So I had a unit tangent. I want to track how much it changes. So the change is the differential of that. I want to track it based on how much I have traveled. If I traveled the long distance, of course there's a more opportunity for changing in this direction. So to make sure that we are doing apples to apples and oranges to oranges, I have to divide this thing by how much I traveled. So I divide by ds. The extent to which this vector is going to be small or big is going to indicate my curvature. To have a number, we take this thing and put it in absolute value. And that is exactly what we call a curvature, and traditionally shown by letter K. So this is going to be the curvature of a curve. Doesn't matter if you are in 2-dimension or 3-dimension or whatever. That is how the curvature is defined. So I hope that you understood what the basis of this definition is. Next is, well, how do you actually calculate this? You can go ahead and get your curve in terms of the arc length. That's why we went through this discussion. Get that in terms of arc length. Find the unit tangent vector. calculate the derivative of that with respect to the arc length and calculate the absolute value of that, and that's going to be your curvature. That typically turns out to be a long order to go through all those steps. So first of all, you have to get your curve in terms of s, then find out the velocity, and then normalize that to get t, then differentiate t with respect to s, and then take absolute value. Typically we run out of breath by the time we get to the bottom of that. So what we are going to do is to introduce you to some alternative formulas that are a little bit more perhaps friendly to calculate. So here are alternative ways of doing this. One is take the numerator and denominator, divide it with respect to, or differentiate them with respect to t. So this is going to become dt, and here also going to be ds dt. We are taking same ratio. Numerator we can show it as t prime. Denominator is just our velocity, so we can show it as r prime or show it as v. So it's going to be ratio of these two vectors. There is still work involved in doing that, and some alternative style of calculating this thing is r prime, that's our velocity, times r double prime, which is our acceleration, and this is cross product. You learn about cross product in Calc 2. Take absolute value of that and take that and divide it by r prime, that's your velocity, cubed. And here's another way of writing this in terms of quantities, perhaps hopefully easier to memorize. That's v cross a in absolute value divided by v cubed. Sometimes calculating cross products is something that needs a little bit of a practice, and let's go ahead and perhaps do one of these things. So these definitions, these formulas, where do they come from? Let me push all of these things to another separate lecture so that this doesn't become extra long and hard to follow. And I'm going to write a couple of other formulas specialized in 2 dimensions. Sometimes your curves are in 2 dimensions. So for our traditional y is equal to f of x, so in 2 dimensions, sometimes most often you write your curves in this style. Your k turns out to be f double prime in absolute value over 1 plus f prime squared to power of 3/2. So this is essentially that, denominator representing this. Sometimes you have so in 2D sometimes your x is parametrized somehow and your y is parametrized somehow, and then your curvature becomes x prime y double prime minus x double prime y single prime, this whole thing in absolute value to make it positive, and the denominator is x prime squared y prime squared, and the whole thing to power of 3/2. So all in all, there are like a half a dozen different formulas. More or less all of them talk about the same thing, and let's go ahead and practice some example. Again, an example that is made to be rather easy to follow, and with some magical cancellations and such. So this is a traditional example. Position x 2t, y t squared, z minus t cubed over 3. So you can go to that software and graph it. It's just some graph. So that's R. And most straightforward perhaps formula would be this one. So that's what I'm going to go aim at. I need my velocity and I need my acceleration, and I need to remember how to do a cross product, and I'll be all set. So R prime is 2 and 2t and then minus t squared. So all I did differentiated each of these three items. R double prime, well, this becomes 0, 2 and minus 2t. Okay, so we say k is R prime cross R double prime over R prime cubed. So you notice that the concept is very intuitive. How tight is the turn? The formula, however, is not that straightforward. So now do you remember how to do a cross product? If I have A cross B, how do I do it? Here's one way. Write I, J, K, and you say this is A1. You write the first one here and second one here. So this is a way of essentially remembering how things are going to run. So I multiplied by the determinant of this. You typically draw diagonals and follow the diagonals, however is comfortable to you. A2, so you want to consult your textbook. For a review of this. J times A3 B1 minus A1 B3, so I didn't make enough room. K times A1 B2 minus A2 B1. One of the formulas that are next to impossible to memorize, but if you follow some conventions you wouldn't go wrong. So what do I have to do is do R prime R double prime. So that's going to be, so I'll have I, J, K again. R prime 2t minus t squared, 0, 2 minus 2t, and you carry out this, so it becomes I, this one times this one. Okay, so that what's that? This times that, it's going to be minus 4t squared, and minus this times that, that's plus 2t squared. And then J times well, minus t squared times 0, that's going to be just 0, and then minus product of this one and that one, it becomes plus 4t. Finally you have a k times this times that, it's going to be 4, that times this one is just 0. So let's clean it up. This becomes minus 2t squared comma 4t comma 4. So I didn't write ijk because they just make it more cluttered. Then I want to take absolute value of this thing. So absolute value, how do you take it? Well, you take them, square them, add them up, take square root. So let's write this in quickly. 4t to power of 4, 16t to power 2, and another 16. Well, this is again another lucky day that this whole thing is really 2t squared plus 4 squared. Is that right? 4 squared, 2 squared, twice the product of these two is that. So we get lucky that things don't stay under radical. That is very uncommon. common situation. So for my numerator, I have 2 times well, that's 2t squared plus 4. That's the numerator. That's not all there is to it. R prime, I have to take R prime, take absolute value of that 2. Well, that's going to be 2 squared, 2t squared minus t squared squared 4t squared, t to the power of 4, and that obviously becomes t squared plus 2. So that's my denominator. So I write the denominator, that's R prime, has to be cubed. We notice in this special case this is 2 times t squared plus 2. This is t squared plus 2 cubed. When you simplify it, you get, let me write it in another color so they don't run, 2 times t squared plus 2 squared. So this is the curvature of this particular three-dimensional curve. What we did was to use this formula, but of course you could have used this formula. I encourage you to read the text to see how that one goes. Same length of work that has to be done in either one of them. So but when the problem is not as magically constructed for all the radicals to simplify and such, perhaps this is what I did right now is perhaps easier, even though that's not the basic definition of it. Okay, let's conclude this rather lengthy lecture by a final statement. This is one of the lectures that easily bridges between this class and certain classes in engineering or physics. If you take a mechanics class in either of those disciplines, you are going to be talking about this topics as well for an object that travels in space. So we are going to next talk about acceleration and its connection to curvature. Well, what's the connection? Well, one of them is quite obvious to you. When you go around the curve on a bicycle or your car or something, you feel that you're bending in a certain direction. You're bending toward the center of the oscillating circle, and the amount of acceleration or force you feel has something to do with that curvature. The higher curvature it is, the more force is going to be on you. So suppose I'm traveling on a curve like this, and here is my unit tangent vector, and then my unit normal vector. These are both of length of 1. So this is my n, this is my t. T is in direction of the velocity, and this is perpendicular to that, perpendicular to the curve. Then I might have some acceleration. Here is my acceleration. Acceleration has 2 components. One, the component called tangential acceleration, that's a sub t, and the other one is sometimes called normal acceleration, that's called a sub n. So the acceleration breaks naturally into 2 pieces. One is a sub t, that's a number. A sub t is a number, times t, plus a sub n times n. A sub t is acceleration in this direction. If you are pushing on the gas pedal, this is going to be positive. You're pushing on the brake, that's going to be negative. This could be positive or negative. This one, if you have any curvature in the road, this is always positive, pointing in that direction. Okay, what are some formulas for this? Again, I'm going to just mention them and postpone the derivation to the next time. A sub t has a simple derivation and the formula. A sub t is how much does your speed changes. So this is the v in absolute value. You have to calculate this speed and then take a derivative of that. Another style of doing this is take a second derivative of your arc length with respect to your parameter. Finally, from just vector calculus, what is the projection of this on that vector? You simply need to take the vector that you want to take a projection of, dot it with your velocity or with t, and then divide it with your absolute value of velocity in that direction. An, the normal acceleration, and that is the projection of this thing on n. It's easy to see that that's going to be a times sine of this angle, and one way to arrive at that is through the cross product. So one way is to write it a cross v over v. Second way is, well, how do you calculate that? Here's another formula from vector calculus, is the following. You see that in calculus 2 divided by the same thing. So it's just a formula for that. And finally, the connection of this thing with curvature. In your physics class, probably you have seen that famous expression v squared over r that shows up in many formulas related to going in a circle and such. Well, 1 over r is same as k, our curvature, and v is just ds dt, that's the velocity, squared. So if you want, I write it here again. So you take the absolute value of your velocity, you square it, divide it by the radius of the curvature if you have it, and that is going to be giving your an. So if you come across some formulas related to that, you have these tools to go after them. Okay, so we still have to explain various formulas here, where they come from, and this is perhaps the highlight of this lecture. Where does this formula come from? But let's keep that for a separate lecture so that it doesn't become too much here. Okay, until next lecture, good luck and God bless.